Imagine sitting in the captain's seat of a commercial airliner. You need to perform a relatively basic task, right? Like turning on the external navigation lights.
Right, something that should be totally straightforward.
Exactly. But instead of a single, clearly labeled switch, the dashboard in front of you has like 400 different switches that all technically control the lighting system.
Oh, wow, yeah. That sounds stressful.
Right. You have acoustic switches, biometric toggles, laser-guided dimmers, touchscreen sliders. You are just completely paralyzed by choice, staring at this massive array of controls, thinking, I just want to flip a switch and see the light turn on.
Yeah, and the irony of having absolute freedom in your tooling is that it often manifests as, well, cognitive paralysis.
Yeah, definitely.
When a system provides too many ways to accomplish a simple job, the operator stops acting and, starts evaluating. You burn all this mental energy just deciding how to act before you've even taken the first step toward your actual goal.
And that overwhelming fatigue from having too many ways to do a single thing is the perfect entry point for today's deep dive. We are opening up a developer's personal journal, specifically, a blog post published today, May 12, 2026, by an author named Ang.
Right, and it's titled Notes on Haskell Programming, Part 133, I think.
Yeah, exactly, Part 133. And while we are looking directly at Ang's personal reflections and, code snippets detailing a specific refactoring journey in Haskell, which is a highly technical functional programming language, our mission today goes way beyond just hardcore coding.
Yeah, it's definitely not just for software engineers.
Not at all. We are exploring the profound intersection of human memory, the evolution of language design, and how the tools we use to build the digital world are being fundamentally reimagined. Because whether you write software or just rely on it daily, that frustration of, too much information and too many ways to do something is a universally human experience.
It really is. Which makes Part 133 of this journal so compelling. I mean, Ang has clearly spent immense time in the Haskell ecosystem.
Oh, for sure. 132 parts.
Right. Yet the friction hasn't disappeared. The tools still occasionally get in the way of the thought process, which highlights a massive flaw in how we historically designed these intricate systems.
Okay, let's unpack this. We need to start with the specific root of Ang's frustration. Ang mentions working on a pet project almost daily, but still struggling to remember Haskell's syntax, playfully citing age as a contributing factor.
Which is super relatable.
Right. But the core of the issue is a concept Haskell shares with older languages, like Perl, which is TMTOWTDI. There's more than one way to do it. Ang explicitly states this creates an alphabet soup problem.
What's fascinating here is the psychology behind that TMTOWTDI acronym. If you look at the history of computing decades ago, this concept was championed as the ultimate expression of developer freedom.
Like it was a feature, not a bug.
Exactly. The philosophical argument was that a programming language should mirror a natural human language. Like in English, you have dozens of ways to say, I'm happy. You can be joyful, ecstatic, over the moon. Language designers thought developers should have that same expressive freedom. But time has revealed that this extreme freedom imposes a massive compounding memory tax on the human brain.
Because in software, you aren't just writing poetry. You are building mechanical logic.
Right, it has to function.
So if there are 10 different ways to extract a piece of data from a data structure, you are forced to hold all 10 variations in your active working memory.
Because you might encounter any one of them when reading a colleague's code or even, your own code base from 6 months ago.
It sounds like trying to cook in a kitchen where you have 15 different types of spatulas. Sure, it's flexible, but sometimes you just want to flip a pancake without having to evaluate the aerodynamic properties of each tool first.
That's a perfect analogy. You spend your cognitive budget parsing the syntax instead of solving the architectural problem. When you sit down to write a function, you shouldn't have to navigate a maze of micro-decisions regarding syntax.
Right, back to the airliner cockpit. Do you leave the lights on?
Exactly. Ang's alphabet soup of competing symbols and overlapping methods is actively obstructing the joy of building the project.
Which brings us to the actual code solutions Ang offers to fix this cognitive overload. Ang refactors the code to use some very specific, elegant language features. Let's look at the first one, which targets a function called convert to ebook.
Yeah, the getter functions.
Right. Originally, Ang was relying heavily on getter functions to extract data. Like you have an object named args holding configuration data.
Sure.
To get the file path, you run a getter function on it. To get the output format, you run a separate getter function.
And that forces the developer to write incredibly verbose, repetitive instructions. You are perpetually interrogating the object line by line. Give me the path, now give me the format, now give me the next variable.
Right. So to fix this, Ang shifts away from those and deploys something called an as pattern using the at symbol. It looks like this args at symbol and then in parentheses args input path equals path, output format equals FMT. But wait a minute, I have to push back here. Ang just complained about Haskell being a cryptic alphabet soup full of confusing symbols. Isn't throwing an at symbol in the middle of a string of text just adding a new weird crouton to that exact same soup?
A crouton, I love that.
I mean, how does this actually make it easier to read?
I get it. It looks entirely contradictory at first glance. You're trying to reduce symbol fatigue by introducing a highly specific, idiosyncratic symbol.
Yeah, that seems counterintuitive.
It does. But you have to evaluate the as pattern by looking at the downstream effects it creates throughout the rest of the function. It's a calculated trade-off. You accept a tiny bit of upfront localized complexity in the function signature to guarantee massive long-term readability.
Okay, so walk me through the mechanics of that trade-off. How does the compiler actually process that single line of code with the at symbol?
So when the Haskell compiler sees that at symbol, it performs two distinct memory bindings simultaneously. First, it binds the entire data structure to the overarching variable name args. But in that exact same computational breath, it reaches inside the structure, finds the input path, and binds it to a localized variable simply called path. And it does the same for the output format, binding it to FMT.
Ah, I see. And Ang explicitly notes how this is used, because right after doing this, the code uses a built-in function called replace extension.
Yes.
It takes that cleanly extracted path variable and instantly morphs it to create a brand new outpath variable.
Yeah.
You couldn't do that as seamlessly if you were still constantly interrogating the args object with verbose getter functions, right?
Precisely. By utilizing the as pattern right at the entry point of the function, the developer completes all necessary unpacking immediately. The alphabet soup is effectively neutralized.
Because the remainder of the function is stripped of all those repetitive extraction commands.
Exactly. It communicates intent beautifully. It tells the machine exactly how to allocate memory, and it tells the next human reading the code exactly which pieces of data matter for the logic that follows.
Okay, so we've solved how to elegantly read data. But reading data efficiently is, only half the battle. If the underlying data structure shifts beneath your feet over time, your efficient read becomes a spectacularly efficient crash.
Oh, absolutely.
And Ang clearly recognizes this, because the next phase of the refactoring focuses on a major pain point for agility. How do you make sure your code doesn't break when data structures change? This brings us to Ang's parse function.
Right, moving from readability to architectural stability.
Exactly. Originally, Ang used positional pattern matching in the parse function. The code was args path underscore verbosity debug underscore. Those underscores are wildcards, just telling the compiler to ignore whatever data sits in those specific slots.
Yes, the wildcards.
I mean, I'm looking at this, and it feels inherently dangerous to rely solely on the geometric order of items in a list. If a developer later modifies the args data type and inserts a new field right in the middle, doesn't this entire change just blindly grab the wrong data?
It absolutely does, and that is why positional matching is so brittle. It creates a hidden, undocumented assumption that the architecture of a data structure will remain frozen in time forever.
Which it never does.
Never. Let's say you have a user profile ordered by first name, last name, and email. Positional matching tells the compiler, grab the third item, that's the email. If someone later adds a middle name field, email becomes the fourth item. Your code will still dutifully grab the third item, which is now last name, and try to send an email to Smith.
And the most insidious part is that the compiler might not even catch it, right? It just fails silently or disastrously, injecting corrupted data into your database for weeks.
Silent failures are a developer's worst nightmare. You spend days tracing a bug that originated from a single, undocumented structural shift.
Wow.
That is why Ang swaps out the positional approach for named record decomposition. The refactored code explicitly declares args, input path equals path, verbosity equals phi, debug mode equals dbg.
Which instantly solves the geometry problem.
Exactly. You don't have to worry about the specific ordering of fields anymore.
So positional matching is like blindly reaching into your suitcase, knowing your socks should be in the top left corner. If someone repacked your bag, you're grabbing a handful of toothpaste.
That's a great way to picture it.
But named decompositions is like having clearly labeled packing cubes. It doesn't fundamentally matter where they sit in the bag or if they get shuffled around. The cube labeled socks always gets you socks.
Right. It establishes a bulletproof contract of certainty. You eliminate a massive source of cognitive anxiety because you no longer have to hold the structural map of the object in your working memory.
Okay, here's where it gets really interesting, though. Even after meticulously implementing these brilliant protective features like the AS patterns and name decomposition, Ang kicks a step back and admits that Haskell still isn't fully satisfying.
Yeah, it's still not the ideal environment for Ang.
Right. And this leads to a theoretical exploration of what the perfect language would actually look like. Ang looks across the broader landscape and points to a completely different language called Elixir.
Right, so Elixir, which inherited its traits from the Erlang virtual machine, is widely revered in the community for having some of the absolute best syntactic support for pattern matching of any language in existence.
It's just incredibly natural for productivity.
Yes, the way you write logic in Elixir feels incredibly fluid and flexible.
But Ang highlights a fatal flaw for these current needs. Elixir is not a systems programming language. It is fundamentally unsuited, or at least less enjoyable, for the low-level projects Ang wants to build. Why exactly is a language that reads so beautiful completely unusable for something like building an operating system?
If we connect this to the bigger picture, it comes down to the eternal struggle of programming language design. The grand tug-of-war between high-level human readability like Elixir and low-level machine performance and safety. Elixir handles complex background tasks automatically to make the human productive. Most notably, memory management, utilizing a garbage collector.
And garbage collection sounds helpful, but it comes with a severe performance penalty, right?
A massive penalty in systems programming. As your Elixir program runs, it generates data that takes up memory. The garbage collector periodically has to pause the execution of your actual program, scan the memory heap, sweep away unused data, and then resume.
So it actually stops the program.
Exactly. In high-frequency financial trading, for example, where times are measured in microseconds, a garbage collector pausing your system for even 10 milliseconds could cost millions of dollars.
Wow. Which is why systems programmers turn to languages like Rust or Go. They provide raw, uncompromising power.
Specifically, Rust provides memory safety without a garbage collector. It enforces strict, complex rules about memory ownership at compile time. There's no background sweeper pausing your execution. But the trade-off is that Rust forces the developer to manage that immense cognitive load.
You have to satisfy the compiler's strict rules, which is exhausting.
Exactly. Or you use Go, which gives you amazing systems-level performance, but again, different trade-offs in syntax and flexibility.
So this brings us to the central what-if of Ang's post. Ang starts dreaming up a Frankenstein language. What if we created a systems language with Elixir's abstract syntax tree? It's AST, but gave it a Rust-like type system for memory safety. Or blended Elixir's flexibility with Go's systems-level performance. Or even just created a new Haskell dialect that brings Elixir syntax directly into Haskell.
Let's clarify that AST part, the abstract syntax tree. When you write code, the compiler strips away the syntactic sugar and translates your logic into a hierarchical tree of nodes.
Okay.
By saying we should adopt Elixir's AST, Ang is suggesting we steal the fundamental structural logic of how Elixir organizes thoughts, regardless of the underlying runtime engine.
Right. And Ang calls this theoretical Frankenstein language a fun and doable project strictly because we are in the age of AI and LLMs. I have to ask, is Ang being wildly overly optimistic here? Or do large language models actually make building a brand new, highly complex programming language a weekend hobby project now?
Well, weekend hobby might be slightly ambitious for a production-ready language, but Ang's underlying premise is spot on. Historically, writing the lexeron parser to construct that intricate, abstract syntax tree could take a team of engineers months.
But now you can just feed the grammatical rules into an LLM.
Yes. Large language models have drastically lowered the barrier to entry. AI models excel at translation and pattern recognition. If Ang wants a language that structurally looks exactly like Elixir but compiles down into strict Rust memory models, an AI can generate the boilerplate for that custom parser in minutes. The heavy lifting is automated.
That is wild. Let's step back and summarize the trajectory of what we've explored today. We started with Ang's deeply relatable frustration over Haskell's alphabet soup and that whole TMTOWTDI memory tax. We watched Ang systematically dismantle that cognitive load with the elegant fixes of the @AS pattern and named record decomposition. And finally, we followed this journey all the way to the futuristic vision of an AI-assisted superlanguage blending Elixir, Rust, and Go.
It perfectly encapsulates the life cycle of software engineering. You solve a micro-level syntax problem, and it inspires you to question the macro-level architecture of everything.
So what does this all mean? For the listener, whether you are configuring servers or just using apps built by teams who do, why does this journey matter?
This raises an important question about the imminent future. We have spent this entire discussion analyzing syntax, the at symbols, the exact placement of variables inside packing cubes. All of this is ultimately syntactic sugar.
An artificial construct just to bridge the gap between human language and machine binary.
Exactly. But if AI and LLMs are becoming so advanced that they can effortlessly generate new syntax or create new programming languages out of thin air to suit our exact preferences,
Wait, you mean,
will human-readable syntactic sugar or even specific programming languages themselves eventually become totally obsolete?
oh wow, you're saying the bridge itself might disappear.
In a few years, developers might stop worrying about syntax entirely. We might simply speak to the machine in plain English, dictating the rules, and leaving the AI to decide whether the underlying code should look like Haskell, Rust, or Elixir. The human operator will just evaluate the resulting application.
That brings us full circle to the commercial airliner cockpit. It's like ignoring the 400 confusing switches, turning to an AI co-pilot, and simply saying, turn on the navigation lights.
Exactly. You don't know which switch it used, and you don't care.
You just get to fly the plane.
Yeah.
And that is a powerful thought for you, the listener, to mull over the next time you're frustrated by the complexity of the digital tools in front of you. The ultimate evolution of technology might not be a better tool. It might just be not needing the tool at all. Thanks for joining us on this deep dive.